Did you ever wonder how the parameters for a model are chosen and how one can evaluate them to determine which parameters are more useful? Yes? Well, perfect for you, because today we are going to talk about the Fisher information, which may solve your problem. To make you a real expert, we are going to derive the Fisher information for the Poisson distribution and taking you along every step of the way. To refresh your memory and build a basis to better understand the derivative later, let us recap what the Poisson distribution is all about. The Poisson distribution calculates the probability of observing an event k times during a given time interval. It is defined by lambda to the power of k divided by k factorial times e to the power of negative lambda. While k corresponds to the number of events, lambda is equal to the mean of all events in that specific time period. The random variable x defines the number of events in a fixed unit. This distribution formula can be applied to that random variable if all events are occurring independently from another as well as randomly, which basically says that the occurrence of one event does not change the probability of another event, as well as that the probability of the events do not change over time. Allow us to illustrate with an example. Between 12 a.m. and 3 p.m. the bus is scheduled 15 times, and we know that on average the bus runs late about 4 times in that time period. Suppose that we want to know how probable it is for the bus to run late 7 times. Now, how would we do this? Firstly, we look for everything we need for the formula. The number of events we want to observe is 7, so we set k to 7. The mean is 4, so lambda also equals 4. Knowing that, we can make use of the function we defined earlier. 4 to the power of 7 divided by the factorial of 7 times e to the power of negative 4 equals 0.05954, meaning that the probability that the bus runs late 3 times more than usual is roughly around 6%. Now let's plot this and take a look at the distribution overall. And as we can see, we were correct. The probability is highest for k equaling 4, which is quite intuitive as it is the expected value. For reference, look at the function when we change the mean. As you can see, does the expected value not only change the highest point of the function, but also the variance. And how do the values change for the different means? Well, they become larger, proportionate to how far off they are from the given k, meaning if the mean is equal to the number of events we want to observe, the Poisson distribution is highest. In this case, that would mean that both k and lambda are 7. Okay, now you should be all caught up on the Poisson distribution, but before we can derive anything, we want to refresh your knowledge on the rules for logarithms. The most important being the calibration and derivation rules. Also note that in the following and pretty much throughout the entire video, we are talking about the natural logarithm when talking about the logarithm, which is ln for short. According to number 1, the logarithm of a product between arbitrary many values equals the sum of all those values with the logarithm taken respectively. The second rule is quite similar, as it states that the logarithm of a division is the same as the subtraction of the logarithm of each component. At last, let us take a quick look at the derivation rule, which shows that the derivative of the natural logarithm of x is defined by 1 divided by x, which might come in handy later. Knowing that, we can finally move on to what you've been all waiting for, the Fisher information. The Fisher information consists of the score function and the maximum likelihood function. Accordingly, the way to derive the Fisher information from a distribution is as follows. First, calculate its logarithmic likelihood function, then derive it to get the score function, and finally compute the variance of that score function to get the Fisher information. But let's take a closer look for the Poisson distribution. And therefore, let's start with the likelihood function. The likelihood function consists of the product of the samples times the Poisson distribution. Therefore, we need to calculate product from 1 to n for e to the power of minus lambda times lambda to the power of k, divided by the factorial of k. Here, our first step is to take the natural logarithm of the likelihood function. By doing that, we can get rid of the product sign. The next step is to take the formula inside the sigma sign apart, which means products will become sums and divisions will become subtractions by the help of the natural logarithm and the rules we defined earlier. Then we take the exponent from within the ln in front of it, and thus getting rid of the redundant ln of e formula. The fourth step consists of disassembling the sigma sign, namely taking the minus lambda in front and just multiplying it by n, which here again stands for the samples. Additionally, we write the other two summands separately. That way we can single out the sigma sign with only ln k of I in it and make it to our final step, which is cancelling the sum of ln k of I from 1 to I out, because it is a constant and therefore redundant for our purposes. After applying all these steps, we are left with the logarithmic likelihood function, which is minus n times lambda plus natural logarithm of lambda times the sum from 1 to n of k of I. The next step to get closer to the Fisher information will be to derive this logarithmic likelihood function, which in return is called the score function. To do this, we make use of the third logarithm rule, which we talked about in the beginning, which defines the derivative of ln of lambda as 1 divided by lambda. The rest is quite easy, as the derivative of n times lambda is equal to n times 1, and thus we get our score function, which is equal to negative n plus the sum from 1 to n k of I times 1 divided by lambda. Now, in order to estimate lambda, we have to maximize our probability function, which means setting the derivative, thus our score function, equal to 0. We will then solve the equation towards lambda. First, we will add n to both sides and then multiply it by lambda. Afterwards, we will divide by n and we'll have our final result, lambda equals 1 divided by n times the sum from 1 to n of k of I. Having that, we can go on to our third and final step towards the Fisher information, which is to compute the variance. We can achieve this by taking the derivative of the score function and multiplying it with negative 1. The original Fisher information equation is called I of lambda equals 1 divided by squared lambda times the sum of x of I from 1 to n. To simplify it, we will then substitute 1 lambda by the equation that we previously computed, which again is lambda equals 1 divided by n times the sum from 1 to n k of I. Afterwards, we will cancel out the sigma signs with its formula, and then we're taking the inverse. Therefore, we are left with n divided by lambda for our Fisher information. Now we are done with the general computations and derivations, but we think that the intuition and interpretation behind the Fisher information will become much clearer when considering our previous example again. So let's just do that. Suppose that Mr. Miller is the chef of a bus company who wants to know how often his buses are late on average. For that, he wants to estimate an average value for the number of delays of a bus in the time interval between 12 a.m. and 3 p.m. On his first day, he observes 10 buses. Those were late about 28 times in total. Whereas on the second day, he inspects 50 buses, which relate about 120 times. To estimate lambda, we maximize the likelihood function. Therefore, we set the score function to 0, plug in the values, and calculate the lambdas. But now Mr. Miller is confused because he gets two different values for lambda. Lambda on day 1 would suggest that a bus riding between 12 and 3 p.m. is late 3 times on average, whereas on lambda for his second day would expect a bus being late about 2 times. So, which value can Mr. Miller trust more? Which lambda is more precise? In order to find out how precise a lambda estimation is, we use the Fisher information. Again, basically plugging in our values into the formula and calculate the Fisher information. But how can we interpret these values? The Fisher information is a measurement to calculate the curvature of the likelihood function. The higher the value, the stronger the curvature, and thus the lower the variance and the range of the values our lambda can take. Hence, our estimated value is more precise for a higher Fisher information. Mr. Miller should therefore trust the lambda estimation of the second day more and can assume that a bus in his company comes late about 2 times in the time interval between 12 a.m. and 3 p.m., which also shows another property of the Fisher information, which is that it buries more information proportionate to the sample size, showing that a bigger amount of observation can tell you more about the event and helps you create and evaluate a model. And with that, that's everything you need to know about the Fisher information and how to derive it for a given distribution. So if you ever have a problem with the Fisher information or estimating the importance of a parameter in general, we as Group 13 will be glad to help you. Hope you had fun and learned something new.